inviting me and giving me the opportunity to speak about the research and development work we do in thin film solar cells. So as I'm introduced, actually I have three hats or three capacities or part of personality. I'm a scientist. I studied in IIT Delhi. I was born and brought up, of course, in India. And then I moved to ETH, which is Swiss Federal Institute of Technology, very well known from where Albert Einstein did his education. And there I started doing research in thin film solar cells. And after that, I also became a professor, and I founded a company, FLISM, which stands for Flexible Lightweight Solar Cells. So I have been able to manage doing fundamental research, applied industry-oriented research at EMPA, which is Swiss Federal Laboratories for Material Science and Technology, something similar to National Physical Lab in India. And the FLISM company is a startup company from my research group. So basically I'll be talking about high performance, lightweight, flexible solar modules, which are quite different from the one which you see often in the market. So I'm not going to talk about all these concerns. You are probably aware of all these concerns, but I will tell you that when we look to the single topmost problem facing humanity for the next 50 years, sustainable energy is the number one problem. Drinking water is the number two problem. There are many problems which are linked to the energy. As you know, very often the war is fought only for energy. Of course, there are various ways of energy, but what we are talking about, an energy which is safe and sustainable and which will be abundant for the mankind to use it for the comfort and to meet the essential demands. So if we look to the energy, sun is the abundant source of energy and existence of mankind. We know our planet Earth evolved from sun and our life is all governed by sun. So within 1 hour, our Earth receives enough energy to meet the global demand for 1 year. So there is no shortage of energy. We have to simply look up to the sky. Sun is shining somewhere. There is no need to dig the earth to bring the fossil fuels or to still go for coal. People say, well, oil and fossil fuels are abundant. There is no shortage of fossil fuels. You can keep on burning, polluting the whole world. But one has to also see the Stone Age. Stone Age does not end because of lack of stones. So we are intelligent human beings. We should use our mind and brain to see what is sensible. And the sensible is to use this abundant solar energy for our benefit of the society. Why this energy is important is that it is independent of any political influence. People can claim the countries, but nobody can claim sun. So it doesn't belong to any country, it doesn't belong to any political party, so it's an independent source. And when we talk about the energy, electricity is the most important part which you need for your comfort. Imagine there is no electricity. Probably I will not be giving this presentation and you will not be having this fan running overhead and this light will be not even shining. So electricity is one of the most expensive also form of energy which we need. Solar cell is a device which directly converts light into electricity. There are many devices which convert light into something else, and from something else you can convert into electricity. But sun rays can be used to heat, and that will be the talk which you will hear after me. And another is a solar cell device which converts directly into electricity. So we are talking about this device which is solar cell, and I would be speaking about first giving a progress in the field, of photovoltaics, which is also called solar module technology, and then thin film photovoltaics. And then I will specifically focus on a very interesting material, copper indium gallium selenide, which is abbreviated as CIGS in the form of thin film solar cells, and what are the key issues, world record efficiencies, and flexible solar cells. And then I will go about how this new and innovative technology is getting transferred on industrial manufacturing, and then I would conclude my talk. So what is a solar cell? As I said, solar cell is a device which converts light into electricity. It is a device made with a semiconductor of two different type of conductivities, P and N type, and it has two electrodes. So what you see is a solar cell basic schematic structure, and when this stacked semiconductor device is exposed to the light, a part of light is reflected, and the part of light which goes into the device material, it is absorbed. It creates electron-hole pairs. Electrons are negative charges, holes are positive, and these charges get separated and they move in opposite directions. So electricity is nothing but flow of electrons in a particular direction, and we have the so-called solar electricity. So this is how the solar cell works. You have a device you expose to the light, it creates electron-hole pairs which get separated because of the internal field, and then you have your solar electricity. So the most popular and well-established technology is based on silicon wafers. This is what you see. So one silicon wafer solar cell is like one battery. It gives you roughly about 600 millivolts or 0.6 volt, and you can connect them in series to get to higher voltage and also to have some current. So this is called a solar module, and you might have seen them installed many places. So what we talk very often is the efficiency, and just to give you an efficiency, that means when there is a very nice sunlight like today, it will have 1 kilowatt per square meter of solar irradiation. So if we have 15% efficiency, and when we have 1 square meter of module, it means we will have 150 watt. So this is just to give you the relevance of efficiency. When we want to use it for practical applications, then we have to talk about the cost, and the cost is given either dollar per watt or euro per watt or rupees per watt. And when we are talking about the electricity price, then we are talking about the price per kilowatt hour, which is also called 1 unit. Here in India, it might be maybe 4 or 10 or 15 rupees per unit. And so when you pay your electricity bill, you normally pay for kilowatt hours which you spend. So all the solar modules which you see can be categorized in 3 types of installations. One is utility scale. That means very large volume, some megawatt or tens of megawatts. Basically, these solar modules are installed in open field, so these are called ground mount systems. So these are very high volume capacity solar module installations. Then they can also be applied on the rooftop of residential building, industrial buildings, and commercial buildings. So they are called photovoltaics applied on buildings. Then there is another category where you use photovoltaic integrated elements. So the roof or the facade, the wall itself is integrated with solar modules. So that is called BIPV. So in India, you see solar module installations are booming, and they are mostly on ground mount utility scale. The building related applications are still not that much popular or not that much in a strong volume yet. So when it comes to about the cost of solar electricity, this is one example. As you know, in Dubai, they have abundance of oil. So one would wonder why Dubai should go for solar electricity. They have oil, but they are thinking for future. Oil will end, and it is it creates pollution. So this is the cheapest bid which has been made of 3 cents, 3 American cents. I think $1 US is roughly about 61 rupees, so you can calculate. So this price of electricity in Dubai is cheaper than the fossil fuel. So it means solar electricity, even in Dubai, which is full of oil, can be very competitive. This was in 2000, I think, 16, and within, in the beginning of 2016 or middle of 2016, actually in May, within 6 months, the progress has happened that the price has gone down to even 1.8 US dollar per kilowatt hour. And that's not in Dubai, but in Denmark, Germany, where there is not so much sunshine compared to India or even like Dubai. So it means solar photovoltaic technology is getting very cost competitive on a global scale on in a conditions where there is not even abundance of very high solar insulation. So when people say, well, whether this technology will work or not, these are the examples that this question on working of the cost-effective, clean, sustainable technology is no more there. The solutions are already there. Now we have to see how we implement them and how we use them for various applications. So in the field of photovoltaics, there are many materials, and these are called different technologies. So one is, which I mentioned about silicon wafer-based technology. This is the most abundant technology. Almost 93% of the market share is taken by silicon wafer-based technologies. And then there are some other new technologies based on thin films and some other new materials which I will be talking about, that how they are useful and what potentials they have. At AMPA, in our research lab, we work on cadmium tellurides, CIGS, castorides, perovskites, thin film tandem solar cells. So our research group of about 35 people are involved in various technologies, but we are focusing today's talk mostly on CIGS. So when we look to the different generations of technology, the first generation of technology, which is about 58 or 59-year-old technology, is based on silicon wafers. It is like single pieces, they are put together. They have been very successful. 93% of the market share is based on silicon wafer, but they have certain limitations, and I'll explain those limitations. That's why we are looking for new materials or innovative concepts. The costs of silicon wafer-based modules have already gone down, and there is limited opportunity to still further reduce the cost. The second generation of technologies are based on thin films. These are very thin coatings, less than the human hair thickness. Human hair thickness is about 50 microns, so we are talking about 1/10 of human hair thickness, which is applied on glass or metal or polymer film. And this is called thin film technology, and when you see some of the TVs, for example, or the glasses which are colored, these are based on thin film coatings. Then if you replace glass with foils, then you have some additional advantages that you can have thin film flexible solar cells, and my talk will be focusing on this type of technology. And then there are some new concepts which are based on organic materials, and I believe they are still far away to reach to the commercialization. These are some of the typical efficiencies of single crystal, multi-crystalline, and thin films. So you see that typically thin film modules are somewhat lower in efficiency, but there is a good reason to work on that. So the efficiency difference of thin film is roughly about 14 to 16% compared to multi-crystalline silicon, which is 16 to 18%. So roughly about 2 to 3% efficiency gap. So why one should work or think of thin film solar modules? First of all, in case of crystalline silicon wafers, one requires roughly about 200 micron thick material because it has a very low absorption coefficient. When we use thin film materials, they have very high absorption coefficient, so roughly 1 or 2 micron material, almost 100 times thinner material, is adequate to absorb all the light which we want to convert into electricity. Then one can have these coatings on glass or on steel or polymer films, and one can make monolithic interconnect modules, and I'll show you what it means. Basically, it looks a very nice, elegant, and fast way of interconnecting different type of solar cells. It has a potential for low-cost manufacturing lower than silicon wafer-based technology because it takes very small amount of energy to produce these modules. And also it opens various applications opportunities which are difficult with the traditional silicon wafer-based modules. So what I mentioned was an advantage of thin film, and most important is the energy payback time. Of course, price is important, but you know, sometimes if your daddy is very rich and he can give you subsidy and support, like solar modules made in China are cheaper than anywhere else because the Chinese government gives a strong subsidy. Somebody can sell at less than the production cost. But what is important, fact is actually the cost is the energy. So what is the energy payback time? And that's what you see here. The energy payback time of cadmium telluride or CIGS thin film solar modules are significantly lower. They are typically 1.5 up to 2 years compared to monocrystalline or silicon, multicrystalline silicon, which is typically about 2 to 3 years when the efficiencies were still low. So what we are comparing about 15% single crystal silicon versus about 11 or 12% cadmium telluride. So despite lower efficiency of thin film solar modules, they have they have shorter energy payback time because they take less energy to produce. It takes a lot of energy to purify silicon from sand to make an electronic quality silicon. So this is what is about the pricing. So when you see the dark blue curve, that is how the price of silicon has come down to now about $45 per watt when the factories are about 100 gigawatt cumulative production. In case of thin film, even at a smaller production of about 10 gigawatt, you have a significantly lower cost. So you don't have to invest very high amount of big factories to reach to the cost competitive level. So this is yet another advantage of thin film technology. And also, this is a very busy slide, but the message which I want to give you in terms of the record efficiencies, with thin film polycrystalline silicon, the efficiencies of more than 22% have been achieved, which is higher than multicrystalline silicon or almost comparable to multicrystalline silicon wafer, which is comparable of area in the research lab. So why we want to work on CIGS thin films is, I will cover simply the key points because it has a high absorption coefficient, and what you see is that the device structure on the left is roughly about 3 to 4 micron. So it's a 1/10 of human hair. We have 4 coatings applied on large area, and it can give you very low energy payback time. It can be as efficient as multicrystalline silicon. This has been shown in the research lab, and it will reach to significantly lower production cost of electricity below 5 euro cents per kilowatt hour, and it will have a significant possibility to give you CO2 footprint reduction. What we are talking about, technologies which will help to reduce the carbon emission. And this type of technology has very low CO2 footprint. So this is yet another advantage of thin film technology. So they are of course innovative. They look very elegant, black, blue, dark blue. So these are the colors which architect like. So what you see is buildings which are used with CIGS solar modules produced from companies Solibro or Mans, and also you see ground mounted installation and also an example of flexible solar modules. There is one successful company called Solar Frontier. It is in Japan, and it is a very quite profitable company, and they have producing a gigawatt solar modules. And when we now compare the traditional solar modules are either based on silicon wafer or thin films on glass. They are heavy and they are rigid. Actually, silicon wafers are very fragile. So if you hold them, you can literally break them like this. So they need very special packaging and very good care until you make the modules out of that. And if you replace the glass with foil, then you have the possibility of making flexible solar module. So if I take the traditional solar module, which is crystalline silicon or glass, 1 square meter will weigh roughly about anything from 12 up to 20 kilogram. It's quite heavy. Sometimes for one person it is difficult to hold. And here what you see is a 4-year daughter of my secretary. She is able to lift this solar module. So it's very lightweight. So this is one very distinct advantage of flexible lightweight solar module, that it is very lightweight and it's flexible and it can be produced with roll-to-roll manufacturing. So these are some of the other summary points which I have given. It's not only about the module weight, flexibility, but imagine if you have to transport a solar module, I mean 100, let's say 1 megawatt, you will need at least maybe 5 or 6 such type of tanks to transport. But if you have a roller type of carpet, you can transport solar modules just like easily in one big lorry or in one car even. And that means you have additional advantages to reduce the cost of transportation and installation. So these are some of the other advantages in addition to what I mentioned before. Another yet advantage is related to the manufacturing, and it is called roll-to-roll manufacturing. Roll-to-roll manufacturing means you take a roll of plastic or metal sheet, which is like a roll of cloth, and you unroll it and you do the coating. How cheap it can become. I'm giving you an example. When you buy potato chips packet, you buy, chips packet which has potatoes and some other chips. It's nothing, it's plastic which has a coating of some metal and some oxides to protect against moisture. These coatings are done on rolls which are 5 meter or 8 meter wide rolls and moving with very high speed. So these are very cheap. You eat the potato chips packet and you throw them in the basket, just win. They are so cheap. So the idea is, can we transform this type of manufacturing for solar modules? It's going to be very challenging. It's like climbing the Mount Everest, but sometimes you have to make an attempt. And in academics, we are in the university, we know you make experiments, you can fall, fail, but eventually you succeed. You keep on trying, and then you get to very ambitious type of concepts. So this is the roll-to-roll manufacturing, which is very innovative, and that's what we are trying to do with the company Fleesum, which I established with my PhD students, and one of our investors are actually Tata Group company from India. So this is the research type of solar cell, and here what I'm showing you, a world record efficiency solar cell, which is 20.4% achieved, and this is independently certified efficiency measured from Fraunhofer Institute, developed in our research lab. What you see on the right side is actually a solar module. These are monolithically connected solar modules, so different solar cells are connected in series. So they are about 17% modules. So these efficiencies are as high as multicrystalline silicon. So in our company Fleesum, we have developed this whole manufacturing machine and plant. Coming from an academic environment, and I would really like to encourage the young students, don't get afraid of. When we did our research, it was a solar cell made on a fingertip size. This was. And coming from the research labs, we are not equipment manufacturers. But we said, okay, my PhD student, we said, okay, we are not going to buy these commercial machines which do not work for these technologies. It will require about 100 millions. You can calculate how many 1,000 crores I'm talking about, 1,000 crores rupees. We said, let's do it step by step. We will make our own machines. And these PhD students, they were very courageous. We said, no matter, we will fail, fine, it's okay, we will try. If we will fail once, we will learn, and then we will tell that, yeah, we tried, we failed, maybe we can do it better. If our effort is sincere, somebody is going to appreciate our failure. So take courage, take your courage, go with your conviction. Don't go for simple things that, yeah, I can buy from here and I have to be afraid of that I will fail, what others will think. No, when you make a very courageous step with all your sincerity. Even if you fail, provided you are able to explain why did you fail and what did you learn, I'm telling you the world is going to appreciate, and that's what happened with our investors in Tata. Our research group is in Switzerland, and here is a company from India who understood what is the innovation in this technology. Despite all the risks, they joined our Swiss investors, and they have invested during the last 10 years continuously to translate from this research lab to a large industrial production of solar modules, which I'm going to show you that this is like a plastic foil which is sandwiched between two sheets. One is on the front and another is on the rear to protect against environmental and mechanical conditions. And so then I'm skipping, I'm not getting into all the details, but basically we have many processes steps, and we have a factory in Zurich which won almost all the awards which any company can win in Switzerland, and in 2016 Swiss ambassador in Delhi also awarded the company. This was very prestigious award actually. So this is an example of this flexible solar module I'm talking about. You might not have seen it. So you see how lightweight this is. This is about 3 meter long and about half a meter wide solar module. It's very lightweight. I have an example here. So I, of course, because of the flight, I cannot bring the large one, but this is how the solar module looks like. So this is a flexible, lightweight solar module. This is smaller in depth, in the width, but you can have as long as 3 meter or 6 meter. When we do the processing on few hundred meters, 200 or 300 meter long roll, which is 1 meter wide. So I'm having a small size sample. After my talk, I'll be happy to show you this type of solar modules. So you can literally keep your solar producing device in your backpack or wherever you want to use them for application, you can use them. Another example on very small application is this one. This is a mobile phone charger. It's a flexible solar module which is laminated on the case, and this is a connector. So literally you have power in your pocket. So when you want to charge your mobile phone, you don't have to look for power point. You can simply plug it in, put it in the sunlight. Half an hour will give you more than 1 hour of charge time. It's not only for mobile phones, but when you need higher voltage or wattage, you can have many such small solar modules. And you know, this is like my wallet. I'm taking from my pocket. So here you have higher power modules. So with this or somewhat larger, you can charge other electronic gadgets. These type of applications are absolutely not possible with traditional solar modules. You cannot carry this type of weight in your pocket. You cannot carry them in a rollable manner. So that's where when I titled my talk, we are talking about innovative and new technology. I'm talking about something which is for future and which is quite different. So this type of solar modules which I showed, they can be laminated on steel and they can be applied on the roofs. This is actually a Swiss village where they are using some metal sheets as a roof. So this metal sheet which you see, this doesn't have a solar module. It has no functionality that simply it provides you a protection against the roof. But when you are able to have a solar module integrated, then it helps to produce solar electricity, and it also helps to reduce the CO2 footprint of the building. In future, we are talking about CO2 footprint of reduction. So these are some of the examples I'm talking about, and what you see that we have here in India, the roofs of steel or metal, they are very lightweight roofs. If you want to install traditional solar modules, many of the roofs will not be able to withstand 10-20 kilograms per square meter of weight. So when you have these lightweight solar modules, you have the possibility to simply put them on the buildings. on the other side, what you see on the left lower part is a very beautiful black aesthetics. Architects like them. So these are some of the examples which I showed. So there are many possibilities, not only for ground mount, for buildings, but also for space applications. If you want to launch a satellite, 1 kilo launching cost takes about 50 to 60 $1,000 for geostationary. So if you have a lightweight, you have additional advantages of solar modules. So these are some of the advantages which one can imagine, and at this point I would like to stop with one comment that it's not that we have reached to the efficiency limit of the solar cells. We can go beyond 20%, and actually in our research group we developed some know-how, and we are working towards 25% solar modules, and then we are targeting towards 30% solar efficiencies, but these are from the research type of devices. So at this point I would like to stop, and I would be happy to answer any questions you might have. Thank you very much. Please use mic.
Hello, sir. My name is Tarun Verma. I'm doing Masters in Renewable Energy in Sydney, University of New South Wales. Being new to this field, it is very good to have nice leaders who have a nice vision of empowering the world with renewable energy. So being a student, we don't have much knowledge. We are here to explore this new field. So can you kindly tell us what is your vision of seeing the world in the next 10 years or 20 years with your inventions of thin film solar cells, so that we'll be having some rough idea of where we are going towards in this journey?
Thank you very much for asking this question. First of all, I would like to answer that my answer might be biased. And there is a good reason for that bias. You know, we are scientists, we are passionate. So it comes the passion. Sometimes, you know, passion comes because you believe in something. And when you believe in something, you try to justify that why this is good. So when we did research for 30 years, I did my PhD in solar cells I was very lucky to be introduced by Professor Chopra in 1980 to do my PhD in thin film solar cells. So I'm very grateful to that. So you start with the passion, you believe in it, and now what we look, the costs have gone down. So earlier solar modules were supposed to be only for space, for satellites. Now we are using for ground. Here is one very nice example. Actually it's a flexible solar module on a straw house. So it can go to the villages. Now when you talk about the technology, two things have happened. The costs have gone down and people have started believing in it. Now it's a little bit of a political will that they should try to see that there are clean solutions available. They don't have to be dictated by the oil companies because these are big companies. So one thing of the big companies is they want to have a control on the electricity supply. Solar is about distributed power. You can have it at your home, your village can have it at home. You don't have to be dictated by big electricity companies. So this gives you a very good opportunity to have a distributed solar generation. Coming to the future, as I said, my answer will be biased because I'm working on thin film technologies which are different from traditional silicon wafer based technologies. Imagine about transportation. We have cars, we have bicycle, we have motorcycle, we have also aeroplanes. No single vehicle is good enough for taking care of all. So different type of technologies and based on different materials will eventually find different solutions. So Traditional silicon wafer-based technologies, they are the market openers. They have done excellent job, and now finding the right solution for right application, like it's ball. With one small ball, you can play table tennis, you can play lawn tennis, but you cannot play football, or with football, you cannot play table tennis. Yeah? So at this time, the future will be really having the right type of technology for right applications. And I bet it is going to be, future is going to be, sun is abundant, So sometimes the wisdom will come and people will use solar electricity.
Hello.
Good morning, sir. I am Vaishnavi. I am a student of class 9, sir. Recently, we are doing projects on solar panel. So we took a panel where the efficiency of the panel was 5 watts. But when we aligned the mirrors in the 4 sides of the panel and kept the panel perpendicular to the sun, we got the output as 8 watts. Is it possible to get more than what the company have rated? And if so, what are the adverse of the panel, sir? What will be the...
Yeah, good. So two things. I really do not know from which company the module has come, but when they give you a wattage, this is done under standard test condition. So the light is perpendicular falling, and the light intensity is 1 kilowatt. So when you're having higher light intensity, there is a chance that you can get somewhat larger power. The second possibility is sometimes they might have given you wrong weighting, wattage. So I really do not know. In principle, it would not be possible from the scientific point of view to get such a high wattage. There must be some other reasons.
And may I know what is absorption coefficient?
Absorption coefficient of silicon is about 10 to the power 3 centimeter inverse, which you might be using it. Amorphous silicon has typically 10 to the power 5 centimeter inverse, but that's a thin film. I suppose you are talking about silicon wafer. They are typically 10 to the power 3 centimeter inverse.
Hello. Good afternoon, sir. Myself Jitendra. We are from TVM Power Solar Jaipur. I have a question mark on solar, that one. You said that the thin film efficiency is the 14 to 16%. Right now we are using the polycrystalline panels of 15 to 70% efficiency, and we also assure in future the efficiency, if 1 kilowatt system is 100 square feet area for 1 kilowatt is required, it will be decreased by 1 meter square with efficiency more than 25%. Right now the consumer having the 16% efficiency. What will we do after 10 years? R&D is going on very increasingly. So what will they will replace the panel, because right now we are having issues from customer. The energy efficiency is going to decrease, and we are giving the guarantee of 90% efficiency for 25 years. We will see the 25 years. Next 10 years we have to just the typewriters to go to the computer. Then what will be happen with that panels? We have to replace them.
Okay. Very good question, but let me also admit I'm not an expert in terms of the real application.
Excuse me,
but
MNRE, Ministry of Renewable Energy, give the guarantee.
I'm going to answer that. I'm simply admitting that I'm not an expert in a commercial sense, but I'm going to answer your question. It's very important to accept where you are expert and where you are not expert. So when they give you every solar module or anything which is having a metal or contact, they will degrade. So 10% power loss is acceptable. And when we give the energy payback time, you calculate the cost with all the considerations that how much loss you will have, where you are going to make the installations. So when you are doing a project today, you are doing the financial viability based on today's technology. It's like about the cars. So when you bought a car 5 years back, is that car useless today after 5 years? No. The next generation of technology will come, but your investment which you are doing for today, it will definitely pay you off. And that is the thing, when I was saying that the political parties have to support all these programs. They should not give this type of reason what you said that, let's wait for the technology to develop. You already have a very cost-effective, a competing technology. to begin with now. So why you want to wait for another 5-10 years? Of course the technologies will improve, of course, like I mean, there was a time when we were not having all this type of possibilities. So were not we giving the lectures? Of course we were giving the lectures. But the question is, if you are making the investment, will it pay it off or not? Answer is definitely yes.
Would like to start solar engineering in our university.
Sorry, I couldn't hear all the... Could you please repeat again your question?
What is the starting point if we would like to start solar engineering in our university?
I think it's a very important question, little bit emotional also. It's very unfortunate that in India, despite of having great potentials, we have not done the manufacturing of solar module technology. Already in 70s, Central Electronics Limited started in the manufacturing. In IITs, all these courses were done. And what you have to do is you have to again start with the confidence. Only difference is that now the level of technology has gone very high. So you have to really start with a very good commitment and be committed for 10-15 years. Because you are going to compete on a very high level. So nothing can be done in 2-3 years unless you really invest a huge amount of money here.
Hello, sir. My name is Pratap Sundar. I have two questions. One question is your product commercially available? Second question is, what is the maximum efficiency achieved in the space applications, such as the solar panels on satellites or the International Space Station? Thank you.
Many questions you have asked. So, no, because the questions can always open another question. Yes, our technology is now ready for commercialization, and we are looking for partners to take our technology. It's a new technology. In the beginning, you require a little bit of a courage to accept new technology. You have to be open for innovation. It's not the traditional silicon wafer-based technology. So we are looking for partners who are keen to accept innovative products. We are also looking for places to do the manufacturing. So it can be anywhere in the world. So yes, we are looking into that. And as I mentioned, one of our investors is from Tata Group. This is a global brand company. Now coming for a space application, a space efficiency is one thing, but for a space, the watt per kilogram is very important. So the traditional solar modules, which I said, they would have roughly about 300 to 500 watt per kilogram as an example, square meter. And this will be having roughly about 2 to 2.5 kilowatt per square meter type of weight. So you have additional advantage of lightweight, but the space market is very conservative market. So it's a small market. Despite of great potentials, we might be a little bit reluctant to go into that market as a commercial company. From academic point of view, yes, it is an excellent thing for a space.
Yeah. Hello. Yeah, I'm Professor Sasidharan from SRM University. So my question is, thank you very much for the very interesting talk in the area of CIGS. Okay. So why I am emphasizing this point is, when we are writing a project to the Indian government in the area of CIGS, what they discourage is the indium is very expensive, gallium is very expensive. Why you are going in this area? But when I listen to your talk, so you have made product from the laboratory to the industrial model. So this is the basic difference. So this is the difference. So
Yeah.
What do you think? How do you overcome this? Is there any data? My second question is there any data available on the what is your efficiency decay and other things over the time, something like that? Can you give
Yeah.
And one more thing, what is the long term sustainability and other things?
Yes. So you have asked many questions, but since you are in the field, I would reply to that question.
Sir, namaskar.
No, I have, excuse
Good afternoon, sir.
But excuse
My
me,
name.
I have to reply to, I would be happy to answer, I'm sorry, but I have to first answer to his questions. So You see, first of all, about the abundance and the scarcity of indium. Yes, indium is in a limited quantity, but the amount of indium which is used in a CIGS solar cell is so small that even if the price changes by 200 or 300 times, it's not going to make a difference of 1 or 2 cents per watt. Yeah, it's a very small quantity and it's not so much sensitive to the price fluctuations. In terms of the abundance, yes, if you want to produce more than 100 gigawatt, it's a big number what we are talking about. Then you have to worry for availability of indium. But when you are talking about, CIGS is not going to empower the whole world. There is going to be different technologies. So the people, when they talk about the indium, I think they have to get a little bit of education, no matter from where they are. Sand is abundant, which gives you silicon. But it is so expensive to make from sand to electronic quality silicon. That's why we are looking for alternative materials. So that's, one has to think, the people are sometimes biased. They don't want to try something innovative, sensible. They say, okay, silicon wafer-based modules made in China are good enough. Why should we look for something else? Yes, with that mentality, you don't have to do any research into new innovation things. You can live in 50, 60-year-old technologies. Now, about the stability, the CIGS solar modules, when they are properly encapsulated, they are extremely stable. Even for a space application, they are more stable than the traditional solar modules. If they are not properly encapsulated, like metal or an electronic component, against moisture it will degrade. So there are various tests, including our products have passed the test for 10, 20 years. So there is no problem on that as far as I'm concerned.
Okay, yeah, thank you, sir, thank you.
Good morning, sir. You have showed us on solar cell, thin film solar cell. Is it a multi-junction one, sir?
No. So what I showed you, CIGS, is a single junction solar cell. So it has based on CIGS material, but the future we are talking about, when I said towards 30% solar cells, these are multi-junction solar cells where one stack of a different energy band gap type of solar cell is stacked on CIGS. So these are the futuristic solar modules. But CIGS is a single junction solar module.
Sir, what transparent substrate you had used, TCO, in that?
The TCO is not a substrate, it's an aluminum doped zinc oxide layer, and the devices are made on polyimide film. One can also make the CIGS on metal film as well.
And my last question, can you make any comment on Jawaharlal Nehru National Solar Mission of empowering India by 100 gigawatts?
I think these are very great ambitious plans, and I'm very happy that India is really thinking in this ambitious things, and this is possible, and this is really worth appreciating. Great plans.
Yeah. Good afternoon, sir. It's a very wonderful presentation from my side. My name is Professor Sivaram from National Institute of Rural Development and Panchayat Raj, Hyderabad. My point is, may I request you to highlight disposable mechanism of panels, solar panels.
Okay. First of all, I mean, this question is easy to answer in India than anywhere else. In India, even the newspapers are sold, you know that. So why would you dispose of? There is question of recycling. So when you were asking about the indium, and I said indium is not a problem, because there are some materials into that. So when the solar modules will run their lifetime, by the way, after 10 or 20 years, they will not be dead. Solar modules will still work, but with maybe 10, 20% lower performance. Once you decide that after 20, 30 years that now I want to replace them, you will recycle the solar module. And there are enough technologies available for cost-effective recycling and use of the resource material. You will not dispose of just like that.
This will be the last question. One more speaker is there, so please pardon us, so that after next speaker will speak afterwards.
Hello, sir. I am Pranali from Kolhapur. Actually, we are thinking to provide energy to hybrid bus by means of solar energy on expressway only. Is this possible when solar battery is low? And is this not possible in non-sunny hours? Then what your suggestion for this consequence?
Good. So, by the way, in Switzerland about 30 years back, solar modules were installed already on the highways. But that was against sound barrier. So that was a sound barrier because when the cars are moving on highways, you produce noise. So you put barriers. So these are solar barriers. You can charge the batteries and you can also apply on the roofs. Right now, I think the technologies of battery storage has to be improved then depending on what is the area available, it would be possible. And these are the futuristic thing one would probably be investing and developing. At this point, these are probably in the development stage.
For initialization of the bus, more energy is required. So if I will provide diesel energy as energy, then when the bus is moving is constantly, then it is switched off of the diesel energy to the solar energy. This is possible in actual practice.
You know, it's about engines. First of all, I don't think that the diesel-based solutions and that same engine will work for solar. I'm not a competent person to answer on the engine technology. But yes, electricity-driven vehicles are there, and how you adapt those electricity-driven vehicles with PV, that's easily possible. But how you convert a diesel-driven engine to electricity engine, I think this would be a little bit of a challenge for me to answer. So,
Thank you very much, sir.
thank you very much. I'm very happy to give my talk here.
Thank you, sir. Next, we have Professor S.P. Kedare. He is working in the Department of Energy Science and Engineering, IIT Bombay. He is working on testing standards for solar concentrators. His role was very important in research, development, design, fabrication, installation, and performance testing of Arun Solar Fresnel concentrating reflector with cavity receiver at its focus, which is now used as boiler in industries. Several units of 5 versions of this Arun have been installed across India, and it's saving energy of around 1,750 kg fuel oil per day for about 250 days a year. I welcome Professor S.P. Kedare to deliver his lecture. Welcome, sir.
First of all, I'd like to thank the organizers for giving me an opportunity here. And this is an interesting session, started with photovoltaic, especially CIGS thin film, which is advanced cutting edge technologies nowadays. And very interesting topic by Dr. Indan ji. I am going to change the gear to more practical, immediate work that we are doing. It's on solar thermal energy. I'm going to talk on technologies, issues and future. I'm going to tell something about the solar radiation, my comments. Then I'll talk to the industrial process heat. So solar energy can also be used for industrial process heat. In fact, that is a more easier and direct way of using solar energy, and there is a lot of potential. Lot of things are already happening in India, and we are almost on the forefront in the world. We are also working on solar thermal power, and there are issues in it, and there are many advantages in it also. So I'll cover my topic on this. to begin with on radiation, as Dr. Tiwari has already told about the solar radiation being abundant, one of the thing in India is we have good radiation. However, compared to last 30 years, the radiation has gone down mainly because of the pollution. So the one that is received on earth in India has gone down a lot by about 20 to 30%. That's what we can see from the data of 1980 and data now 2010. There is a significant difference basically because of the brown cloud that we have on India and China. So whenever you design a solar system, it should be based on the ground data rather than on a web data or typically satellite data. So that is one thing I would like to highlight. Okay, let's begin from this. We know that there are solar water heaters. Solar water heaters are widely used. They are used and there are evacuated tube collectors. Both of them go only up to 60 to 80 degrees Celsius. They are widely available. Evacuated tubes are available from China. About 80% of the market is from that. You are aware of this. They are used for water heating, cooking and other things. However, can this be used for industrial process heat, which has typical requirement of about 80 to 100 degrees Celsius plus, minimum 100 degrees Celsius. It goes up to 200, even 300 degrees Celsius. So can we use solar energy for that? Is it economic? So these are the various industries with different materials, either air or steam or water. They use this energy as heat. So there is a boiler or air heater or water heaters. So is it possible to use solar energy in this question, in this situation? That is the question. Also there is a lot of hospitality sector, there is a lot of energy consumption in laundry, cooking, cleaning. These are the normal day-to-day activities immediate to us. Can solar energy be used for it? And these are the typical temperatures that are required. So our water heaters and evacuated tubes are typically not useful for these applications. Third thing is comfort cooling. Typically we experience that when there is more sun we require more cooling. So this is a good application of solar energy. So this can be done by vapor absorption system where heating a generator is a sense refrigerant generator can cool the system, and if the generator is at higher and higher temperature, it's better. The COP kind of efficiency is better at higher temperature of generator. So can this be done? Just another example is cooking in household or community cooking also requires the energy at this temperature. So can we use this energy, because most of these applications we use oil which is imported. 80% of the oil is imported today. These are mainly in medium industrial units where land is available to put solar panels, solar systems. Typically we have to aim at about 10 bar, which is 180 degrees Celsius. We have a lot of skill, so concentrators can be used. So the main thing is if I have to go to 180 degrees Celsius, flat plates are not okay. We have to concentrate the energy by some reflector, lens or something like that and go to high temperature. So these are a bit complicated systems, tracking is involved, but they can be fabricated because we have a lot of skills at lower cost compared to the world. So about 20 years back we have started, many people started, 2-3 groups started in it, and we have started working on the concentrator. So I'll just explain what is this concentrator for the students and other participants. Concentrator is basically a parabola. Parabola is at the heart of the system. A parabolic reflector has a property that all parallel rays parallel to its axis concentrate at its focus. So this property can be used in 2-3 different ways. This parabola can be used and rotated to get a paraboloid structure with a point focus, or it can be extruded to make a parabolic trough with a line focus. Further, this can be broken into pieces, brought on a ground on a flat surface. This becomes a LFR, linear Fresnel reflector, or it can be or the paraboloid can be broken into pieces, brought on ground, that becomes a heliostat or Fresnel concentrator. So these are the four basic types of concentrators which are used. They are used for paraboloid as dish system with Stirling engine at its focus, or solar tower system with a central tower receiver going to high temperature, or parabolic trough which are very common with a line focus system, or linear Fresnel reflector. Each one has different scales, different costing, different limitations also. All these systems, when we compare, there is a basic equation that efficiency is given in terms of optical efficiency into the solar radiation received minus losses. So we work on this equation. In fact, much more detailed form of this equation we use, and various components are identified so that we can identify how our system can be improved. So this is a basic form of equation, efficiency split into optical efficiency and loss coefficient. The one important thing about this equation is that, well, you can see the first term can be constant if I have optical efficiency as constant, but the second term is sensitive to temperature. So if I operate the system at higher and higher temperature, the losses are more and more and the efficiency goes down. So we have to handle this when we need to operate at higher temperatures. This equation put into a graphical form shows that as the temperature increases, efficiency drops. And as Dr. Tiwari has rightly said, there is no one single answer. For different applications, we have different ways, different devices, different concentrators. For different temperatures, we will have different concentrators. So for example, if there is a swimming pool heating, I won't use concentrator. But suppose I want furnace melting of iron, then I cannot use flat plate. So there has to be a choice of concentrator depending on the temperature application and some other considerations also. So this is the gamut of solar concentrators. In India, we do manufacture concentrators. There are 4 or 5 leading manufacturers. This is a system put in NICE, National Institute of Solar Energy, which is at Delhi, south of Delhi, Gurgaon, near Gurgaon. So this is installed for 100 kilowatt of cooling. It is 26 TR system, parabolic trough, Indian made, with tube without evacuated tube, and oil is circulated, and lithium bromide system is used to cool the space inside the office of NICE. This is a Scheffler cooker. You must have been aware of this name. Scheffler cooker is a part of a paraboloid, and it has an interesting property that its focus is fixed on ground. So we can have a focus inside kitchen and we can cook the solar system. In a large scale, we can have many of them generating steam, and that steam can be used for cooking cooking in large scale through steam handling devices. This is linear Fresnel reflector installed at a company in Coimbatore, about 800 meters square, in which mirrors are installed on ground. They are differentially inclined and tracked around that circular trackers, and you can see at the top there is a receiver here. So these are the two receivers on which this mirrors reflect all the energy. So we can pass water through it and go up to the steam. We can go to 250 bar, we can go higher with this. This is a spherical bowl. This is at nearby Pondicherry. This is in Auroville near Pondicherry. This is a 120 meter square, 15 meter diameter spherical bowl with a receiver, which is, so the lighted part, this part is actually a receiver. It's a coil through which water is circulated, and 140 degrees Celsius steam is generated through this system. Here the bowl, the reflector is fixed and the receiver is tracking. So there are various kinds of it. Then we have 2-3 different designs from different companies of reflector, a 90 meter square reflector, there is a 25 meter square reflector which has a paraboloid shape. One of the interesting design is the Arun solar system, which we had researched on and commercialized, the structure need not be paraboloid in this case. So structure is flat and the mirrors are mutually inclined to get the parabolic effect, so that the quality control is very easy, cost can come down. So this is being used as solar boiler up to 10 bar or even higher temperature in industry. This is again a picture of the same Arun system, 160 meter square at NTPC Netra, Greater Noida, where it is used for cooling. It's about 50 TR cooling is there, 200 kilowatt cooling. This is at Akshardham in Delhi, 100 meter square system. So where all these reflectors mounted on a flat surface concentrate the sun rays at the focus, at a receiver at the focus, where it is boiling into steam. So it's a boiler, it's a solar boiler. We go through the IBR process and other things. So this is the application of solar energy for industrial processes for boilers, and we have come a long way. We have been doing it. Some of the pitfalls is we have to select a concentrator for the application. As I said, depending on the temperature, what is the concentrator to be used has to be selected. Again, depending on the load characteristic, is the load during daytime or during night time? Accordingly, the system has to be selected. Should there be a storage or not? We also need to have solar radiation data. If the radiation is very low, then it's not economic to put the concentrator to generate heat. Also, what is the fuel saved? If the fuel saved is costly, if it's oil, if it's gas, it's a costly fuel. So saving it is more economic. However, if I am using it for coal, then there is a problem. Then economics is not that good. So I have to look at the fuel being used in the industry. But at present, about 30 to 35 industries in India are using such system. I will go ahead. One of the challenge here is the integration. The solar energy has its own whims and fancies. It's available only during daytime and there are cloudy hours. But industry cannot agree to that. Industry works 24 hours or maybe sometimes early in the morning, or only small hours it will require the heat. So we have to optimize the integration. How much storage to be provided, how much collector area to be provided. This needs to be done, and this graph shows that a allowed combination of collector area and the storage is studied by optimization methods. One more thing about this application is cogeneration. Here in Ramnathpuram, Tamil Nadu, south of Tamil Nadu, a Coimbatore company, KGDS, has installed this system which generates steam at 40 bar and generates power, and then the spent steam is used for desalination. So in the Ramnathpuram area where there is a drought, the sea water is converted to potable water by this system, and 24-hour system is installed there. So this is also an interesting application of solar thermal energy at high temperatures with concentrators. With this background in India, we have a lot of work done by various industries, various groups in concentrator. We are now looking forward to the solar power systems. The issues are how is the ground performance? Can we assure the ground performance? What is the cost? At what cost? Of course, for oil or gas replacement, these systems are economic, 2 or 3 years payback. But all depends on the site data. One of the major challenge today is reliability of these devices for long term, 10 years, because these are moving systems, complicated systems. So a professional engineering needs to be done. So this is the problem about the industrial process heat, and with this experience we are now going to solar thermal power. You will ask me what is the relevance of solar thermal power. So one of the issue is solar thermal power is costlier. Okay, compared to solar PV, solar thermal is certainly costlier. It's about 14 to 25 crores per megawatt is the installation cost, compared to solar PV of 6 to 9 crores per megawatt. So it's about 2.5 times the solar PV cost. However, the capacity factor is about 1.5 times. So solar PV works for 1200 to 1500 hours a year, but this will work for up to 2000, 2500 hours per year. So that, but it doesn't really make up that much. So what is the relevance of it? So before that I'll explain you what is this solar thermal power. Typically a concentrator, on the left we have shown this concentrator. Oil is heated and the hot oil is circulated through superheater, boiler and preheater, by which steam the turbine is generated. So it's a normal thermal power plant. Only thing is steam is generated by solar energy at that temperature, maybe about 400 degrees Celsius or something. And then of course there are other power systems. This can also, in the night the oil is heated by hot oil, it can be heated by hot oil. So we get the power throughout day and night. Other possibilities with the heliostat, as I said, central tower systems, they can concentrate their solar rays onto a receiver and then we can heat molten salt to very high temperature of 565 or 600 degrees Celsius, and this can be stored. So this is one possibility that solar thermal technology opens up, that we can store thermal energy and generate even at the night. So the problem of peaking and problem of continuous power supply as a base load can be addressed by solar energy. That is one of the major things. One of the issue is, as we looked at the graph previously, as temperature increases, efficiency of the solar plants decreases. But as temperature increases, turbine efficiency increases. So we have to decide at which test. Should we operate at lower temperature? If I operate at lower temperature, I will get more energy, but the turbine efficiency will be lower. If I operate at high temperature of say 500 degrees Celsius, turbine efficiencies are good, but then solar efficiencies are lower. So we have to strike a balance and optimize the system. So this is one of the design issue in solar thermal power plants. We have 3-4 power plants in India. This is Acme Solar at Bikaner, 2.5 megawatt operating at 1.5 megawatt. This is heliostat bed. You can see the mirrors distributed all over the ground and a central tower on which all the mirrors reflect the energy. This is parabolic trough, Godavari Green Energy at Nok in Rajasthan. This is Reliance Ariva system at Dursar, 125 megawatt. This is a LFR system. So we have all three types of system, and one of the system that we at from IIT has designed and installed at NICE in Delhi is a combination of technologies. That is, on the right you can see the LFR system, on the left you can see the parabolic trough system. LFR systems go to lower temperature of 250 degrees Celsius, but they are more economic. So it generates steam by that, and by parabolic trough heat oil to 400 degrees Celsius, superheat it, so that you can get better efficiency from the turbine. So this combination is unique. Nowhere in the world people have done this, but we are running plant on this system. And there is a test center also. On the right you can see a building, small building, which is a test center. This is the data that we actually generated the power on that 27th May 2014, and you can see that it has gone up to 600 kilowatt for some time, 2-3 hours. This is another interesting system. We are using 64 meter square Scheffler system, which is now installed, and now turbine is being rolled with the ingot of 3-ton iron at its focus, through which pipes are circulated, so that we can heat the iron block during the day, and in the night we circulate water and get steam. So this is a 1 megawatt 24-hour plant that has been installed by Brahma Kumari Ashram at Abu in Rajasthan, and it is almost commissioned now. Turbine has been recently rolled, so they will go online soon. So as I was saying, issues are like this. It is costlier. So our energy target is energy cost target is up to 6 to 7 rupees per kilowatt hour. If solar thermal can meet that, then it makes sense. However, one of the advantage of solar thermal is dispatchable power, in the sense that it can act as base load. It can provide from 8 o'clock, 6 o'clock to 8 o'clock or 9 o'clock in the night. That is an advantage of solar power. This solar PV or wind cannot do unless there is a battery or compressed storage, which are inefficient by itself. So 24 by 7 supply is possible, and many people are now working on it. For this we have to work on heliostat controls, we are working on cavity receivers of new types. Storage material is molten salt, so we have to learn to handle it. There is LFR based PCM storage is to be used. Again, salt is melted and solidifies, and the heat required for it is stored and recovered. Integration of different solar fields, optimization of the field, these are the various technical challenges that we need to address, and people are trying to do that. Cost is another issue. So while doing this, the cost should not shoot up, but one of the thing is, most of the parts of the technologies, almost all of the parts of the technologies are available in India, and we can 100% indigenize. So we are not dependent on any other country. For example, silicon based PV panels are at present 100% imported from China. So there is a lot of activity, but it is not encouraging the local economic activity. So this is one of the problem of silicon based solar. So this system can also address that, provided the last point is if we can develop this engineering and fabrication capacity here. So there are various groups which are working on it. IISc Bangalore through its Sirius project, it's a solar energy research in India and US system. Heliostat design and farm layout. So heliostat, what should be the size of heliostat, how does it track? These are the issues that they are trying to handle. Supercritical CO2, supercritical carbon dioxide is an interesting variation rather than the steam system. Instead of water converted to steam, you can have 300 bar pressurized carbon dioxide heated to 700 degrees Celsius, and that can be used as a material for transfer of heat and extraction of power from the turbine. So this is what IISc Bangalore is working on it. This can have very high efficiencies of 50% plus. So this is an advantage of it, or maybe 60%. Molten salt loop, having a molten salt loop, what are the materials, how to handle it, what are the pumps and other equipment. So these are the issues that IISc is working. IIT Jodhpur is working on dust level, dust deposition, degradation of the receiver and reflector, tracking of heliostat. BARC is working on another concept called beam down heliostats. So all the heliostats concentrated on a mirror at say about 50-meter high tower, and that mirror is shaped such that all the energy is again brought down on the ground, so that the boiler and all system storage can be at ground. You don't have to pump anything. So natural circulation molten salt receiver, they are working on it. In IIT Bombay, we are working on high temperature cavity receiver with coiled tube, which is not typically used. We are also working on PCM storage in this Sirius project. We are also working with NTPC because they are the power generators. So if some of their heat is replaced by sun, then we can save a lot of coal emissions and other things. So on heliostat tracking, Fresnel optics especially, because all over the world the receiver heliostat is actually curved. Instead of that, can we have Fresnel optics so that flat structures are used. Molten salt loop with plated receiver. This is a new concept that we are working on it. Thermocline storage, in the sense that instead of 2 tanks for storage, we can have 1 tank and a layers of heat in it. So that is one possibility. Hybridization of 2 systems as well as phase change material storage. So these are the issues that we are working on it. In India, we see that 24/7 power can be available through solar, which can have a dent on the power scenario by renewable. Otherwise, that is considered as a problem with renewable, that it is not available at demand. Whenever sun is available, whenever wind is available, only then power is available. Instead of that, through storage, we can generate power whenever we want. If there is peak, we can supply to that. That is what is the aim of all of us. I will take 5 minutes to explain this concept of storage. Typically what happens is this graphs show the energy developed by solar system throughout the day. On the x-axis is time of the day. So by 8 o'clock, 9 o'clock, sun has risen and we generate good power, and then sun sets at about 6 or something, so 5 to 6. So this is the energy generator. However, when I feed it to turbine, say for example, for a given field 7 megawatt turbine can operate, minimum rating is 30 to 25%. So this is the minimum steam rate that it can absorb, and this is the maximum steam rate, blue one, that it can absorb. So energy above it is wasted and energy below it is also wasted. So morning up to 10 o'clock or 9 o'clock energy is wasted, and after 5 o'clock energy is wasted. Not only that, the noon energy is also wasted because this cannot be absorbed. Instead of that, if I have storage, then I can have a 2.5 megawatt system running continuously. Say for example, this 2.5 megawatt has minimum steam flow rate at this level, white dotted line. So I can start early at 8 o'clock and end at 6 o'clock. And anything above it can be stored and fed in the night. So that is how we can optimize. Typically the numbers show that if I optimize without storage for a given field, I get about 10% variation in the generation if I optimize it. So instead of 7, if I put 3 megawatt, it will generate less. Instead of that, I put 10 megawatt, it will generate less. So there is an optimum value for 7 megawatt for this field. But suppose I run it with storage, I can generate 10% more. So instead of 15,000 megawatt hours per year, I can generate 16,000 megawatt per year from a 3 megawatt plant. So this is what the storage plays a role. So mastering handling of storage, controls of the system, this is what we are all working on. In this, of course, we are also globally partnering various agencies, mainly for testing lab, reflector testing, life of reflector, degradation of it, improvements on critical components, especially reflector, is what we are collaborating through NTPC, through IFC or various projects. And one of the major issue that we need to face is that awareness. In a way, that's why I am here, that see, this can be done. Solar energy can go up to 100 degrees Celsius, 200 degrees Celsius. We are now thinking of 565 degrees Celsius. So solar energy can generate this, and we can use it effectively even during in the industry. It's not only for power. A normal industry can use solar energy and save a lot of oil emission now. It's nothing in future. So this is what we are working on. If the mass comes in, we work on various issues together, and we can accelerate the development very fast. So that is what I have to say. Thank you. Thanks for patient listening. Any questions? Yeah, 1 or 2 questions, please. Okay, so fine.
Thank you, sir. Now, I request Srikant sir from audience, he is from Sansya Renewable Energy Consultants, to felicitate the speakers. Sir, Professor Ayodhyanath Tiwari, thank you, sir, for coming all the way from Switzerland and telling us about the thin film solar cells. Thank you, Professor Kedare, for telling us about your solar thermal concentrators. Thank you all. So we now close the session here.
which is 10 times lower than the commercial catalyst, and still it behaves as close to the commercial catalyst. Now there are other techniques which further substantiates that our electrocatalyst is usable, is some electrochemical characterization which also depicts the mechanism in which the electrocatalyst can function. And we found that all these materials which we prepared undergoes a 4-electron transfer mechanism, which is the most effective way in which the reaction can take place in a fuel cell. So, yeah, for example, when electrocatalyst does not work properly, it undergoes a 2-electron transfer process, which is not effective, which is not efficient, and leads to lot of other byproducts. Whereas when it goes to the 4-electron transfer, which is proved by this technique, we see that the material, though has got very less amount of platinum, can undergo the 4-electron transfer, which substantiates the previous results. And finally, summarizing the overall effectiveness of this method and the electrocatalyst, we see that these are various other quantitative measures to prove that the catalyst is good, is workable as a electrocatalyst. We see that the graphite-based electrocatalyst is in par or little more than that of the commercial catalyst with 58% of platinum. And the CNT-based catalyst is far higher and is almost touching the range which the DOE or the Department of Energy has projected now. So now the next step is to understand the durability of this electrocatalyst. So we cycled the electrocatalyst for 500 fuel cell load test, and we found that the material does not lose its strength even after 500 cycles of load test. So 500 cycles is a little lesser as of now. Still the experiments are continuing, and we have proved that this material will be a useful material for the futures to come. And in conclusion, I would like to point out that this is the first report in generation of metal nanoparticles without any chemicals, without any sacrificial reducing